Analogy of gradient vector. What is differentiation? What is derivative? What is gradient? Gradient vector, gradient vector, that is something that always lands in area of confusion in calculus. What is a gradient vector? If I have algebraic equation fx, fx is a algebraic equation function over independent variable x. I have algebraic equation fxy over independent component x and y. Then what is gradient vector? What is derivative of fx? Derivative of fx is dfx by dx. dfx by dx. What is derivative of fxy? There is no straightforward answer. What is derivative of fxy when there is two independent components? What is derivative of fxyz if there are three independent components? Then derivative always happens along a certain direction. Integration always happens along a certain direction. It's, it's obvious. If I have a function fx and I am calculating integration, means fx into x, that is area, that is integration. If that is integration, means we can also say that we are calculating area of fx along x-axis, that is the another side of the area. Differentiation, if I have a function gx and I am calculating the differentiation, then differentiation along x-axis means I am dividing gx by x. So integration along a particular axis, it's also possible. Integration along a particular axis, derivation along a particular axis. So derivation along particular axis is also called directional derivative. So derivation along x-axis, it is called partial derivative. It is multivariate. Derivation along y-axis, it is called partial derivative along y-axis. Okay. So these are integration along a particular axis. So this is also called line integral. Line integral along a particular direction. By default, if I say I have fx and I am calculating integration, then by default it is x-axis. But line integral is possible along any direction. Like that, directional derivative is possible along any direction. If it is along x-axis, y-axis, then it is also called partial derivative. So these are the concepts. So derivation, how it is different from the gradient vector. So these things are that we will see. Gradient vector also called vector field. Consider fx equal to x square. Fx equal to x square. What is derivative of fx? That is 2x. Derivative of fx is 2x. This is x-axis. If this is x-axis, then this is x square. This is fx equal to x square. If that is the case, that if I calculate the derivative, a derivative itself is an algebraic equation, that is 2x, then what is 2x? Generally, 2x derivative is also called slope. Slope means at this x, the derivative is tangent at this position, tangent at this position, tangent at this position, tangent at this position. Okay, that is the scenario. What about gradient? What about gradient? What about gradient? Gradient vector. Okay, What is the equation? Y equal to x square means x square minus y equal to 0. Then you have to derive it partial derivative along x-axis, partial derivative along y-axis. Then it becomes 2x, that is partial derivative along x-axis, and partial derivative along y-axis is minus 1. 2xi minus 1. 2xi minus 1 j. 2xi minus j. This proves that if I want gradient vector at any point here, then what is x? X multiplied by 2. Then if x is 1, then 2i minus j. 2i minus j. If it is 2i, then little bit along the negative side of the y. Can you see this is perpendicular? Okay, if x is 10, then 20 minus j. More or less it is along x-axis. Can you see? It is, if it is along slightly tilted, then it is like perpendicular to this. This is gradient vector. Gradient vector is a vector which is perpendicular to the curved line. That is called gradient vector. Okay. What about the reality of what we are doing? What about the gradient vector of a line? Now we have now y equal to x square. Then x square minus y equal to 0. Then 2x minus 2xi minus j is the gradient vector. Gradient vector, whatever vector you see, the gradient vector, whatever the line curve you are taking, the gradient vector will be perpendicular to it. Consider a circle, our famous example, a circle. A circle has equation x square plus y square equal to a square. Okay, before I proceed, now it's different, right? If I say dy by dx, the slope, then any moment dy by dx is a tangent at that point. Whereas if I take gradient vector, dy by dx is also called gradient. But if I take gradient vector, then it is exactly, we did 2x 2xi minus j taken as gradient vector. Now what about the gradient vector when x equal to 0? It is minus I minus j. So if this is the origin of if this is the origin, if this is the origin, at this origin the gradient vector is exactly minus I. Can you see where there is no x component, but slowly the gradient vector is becoming like this and slowly it becomes flat. If that is the case, then gradient vector is always perpendicular to the curve. This is gradient vector. Okay, now we are kind of talking about calculating the gradient vector. What about circle? If it is a circle, then it is x square plus y square, plus y square equal to a square. Y equal to square root of a square minus x square. Okay, leave that. Now x square plus y square, equal to a square. What is two partial derivative along x-axis, along y-axis? Then it is 2xi plus 2yj. If that is the case, then that is the vector. It is same as xi plus yj. If that is the case, then if this is x-axis, then here the point is a comma 0. At that moment it is 2ai plus 0. Whereas here the gradient vector is x-axis itself. Can you see this is radial and perpendicular to the curve? If curve is x square plus y square equal to x square plus y square equal to a square, that is the curve, if I consider it as function over y, then f function over y, then fy equal to square root of a square minus y square. Okay, what is dfy by dy? Dfy by dy, that is minus y by square root of a square minus y square. If that is the case, then if I set it to 0, then y equal to 0. dfy by dy equal to 0, means the slope along y-axis, if I take differentiation, that is along y-axis, dfy by dy, then if it is 0, means there in the curve has no slope along the y-axis at point y equal to 0. So if this is x-axis and this is y-axis, then y equal to 0 is x-axis. Then at this point, if this is x-axis, then at this point when y equal to 0, at this point this curve has dfy by dy is non-zero. But slowly when coming, then here the curve, this point particular, this curve is parallel to the y-axis. If curve is parallel to the y-axis at this point, and gradient is completely x-axis, means gradient is perpendicular to the curve at least at y equal to 0. So gradient is actually perpendicular to the curve line. I'm not talking about any vector. The curve line what we have now, the curve line with that gradient vector is always perpendicular. So that is what we are seeing. Now try with the x square plus y square, the kind of a circle. X square plus y square equal to a square. Gradient vector, I mean we are taking the example. So gradient vector is 2xi plus 2yj. So that is the gradient vector. So when x equal to, at now if this is x axis, this is y axis, at point 0 comma a, at point 0 comma a, then it is 2x, then it is 0 plus 2aj. 2aj means along the y axis when it is hitting this point gradient vector is exactly 2aj along the y direction. So gradient vector here on x-axis is along x direction. Gradient vector here along y-axis is along the yj direction. What about the gradient vector at any point xj, xy? Then it is 2xi plus 2yj. Okay. Now if I take 45 degree angle, then the x component and y component of the gradient vector will be same. If that is the case, then this radius line, if that is the case, then this radius line, if it is same, then this radius line, okay, the equation, if both are same and both are considered, both are kind of alpha, then it is 2 alpha I plus 2 alpha j, means it will be like 45 degree going along the radius. So radius, the gradient vector of any curve is perpendicular to the curve. If I take a circle, the perpendicular to the circle curve is radius. Okay, so how we can prove it? It is perpendicular. We have proved it. We can prove it through vector signs also. Let's consider the fx equal to x square, y equal to x square, y equal to x square. If that is the case, then if this is equation of a parabola. So if this is x-axis, if this is x-axis, if this is x-axis, then this is y equal to x square. If this is x-axis, then it is y equal to x square. If that is the case, then consider any point x comma y, any point x comma y. This is origin, any point x comma y. If that is the case, then if I Okay, I'll change it. So this is x-axis. If this is x-axis, this is the case. If there is any point P, then from origin I, I draw a straight line at P. This is x comma y. If this is x comma y, then the vector, the position vector of the P is xi plus yj. Xi plus yj. Now xi plus yj is representing the parabola. Xi plus yj is representing the parabola. If that is the case, then y equal to x square. Then it is xi plus x square j. Xi plus x square j. Now, if that is the case, then what is its gradient vector? Xi plus x square j. What is its gradient vector? So gradient vector would be I plus 2xj. Okay, so gradient vector x plus 2x square j is the position vector is the position vector of the is the position vector of the parabola y fx equal to x square. So at any point, so if I take point here, then if x is 10, then y is 100. Okay, so that is the vector that is going on. Okay, now if I calculate the gradient vector, then gradient vector here, okay, so if it is a kind of x plus x square j, the gradient vector will be xi plus x square j. So gradient vector will be I plus 2xj. I plus 2xj. Okay, so I believe we are kind of missing something. So if it is if it is a x square, uh, okay, so let's take another example. Okay, we'll come back to it. Okay, so let's take that I have a circle. I have a circle. Then circle, the kind of the equation, if this is x-axis, any point P on the circle, any point P on the circle, okay, if I take any point P on the circle x, okay, if I take any point P on the circle, okay, in parabolic situation we had equation as y equal to x square. So the net equation that came is, okay, we'll see it. Now consider the circle. Consider the circle. The circle equation is x square plus y square equal to a square. If that is the case, then y equal to square root of a square minus x square. If I take any point on the circle, then let's draw it as a position vector. If this is x-axis, this is x-axis, and if I take any point P that is x comma y, then this is the position vector, that is the radian. So that position vector P, so P, the point P equal to xi plus yj, xi plus yj. Okay, let's move back to the parabola. I'm not satisfied, whatever it is. Let's try back again. So, so in the parabolic case, we have, if I take, okay, now if I, this is the case of parabola where y equal to x square. If I take any point P and draw a position vector, then position vector is xi plus yj. Position vector is xi plus yj. If that is the case, y I'll replace with the x square. So it is xi plus x square j. That is the position vector. If you change the x position vector, it will start like this and position vector will start changing, but it will rise rapidly. along the y direction. What is the derivative of this? What is the gradient vector for this? Let's do the derivation along the x-axis. Okay, so the kind of its gradient vector would be I plus 2xj, I plus 2xj. If that is the case, then gradient vector when then along the x-axis, gradient vector is always 1 I plus 2xj, whereas along y direction, gradient vector is changing rapidly. It is going like this. Okay, so if this is the position vector, okay, if this is the position vector, consider x equal to 10. When x equal to 10, the position vector is 10i plus 100j, means this is the position vector. If this is the position vector, now at position 10, x equal to 10, what is the gradient vector? Gradient vector is I plus 2xj, I plus 20j. So at this point, I means this and j means this. So gradient vector is something like this. Okay. So what you are saying? Okay. If I am here, okay, if consider x equal to 5, if x equal to 5, x equal to 2, then position vector is xi plus x square j, 2i plus 4j, 2i plus 4j, 2i plus 4j means it is kind of, it is not 45 degree, little bit higher. This is the direction of position vector. If this is the direction of position vector, what is the gradient vector? I plus 2x, that is 4j. Gradient, if this is little bit, this is position vector, then gradient vector is even higher. If this is position vector, then gradient vector is okay. So I'll try it. So the position vector of parabola is xi plus x square j. If that is the case, then consider x equal to 10. Then it is 10i plus 100j. 10i plus 100j means along the y direction it is 10 times higher. Means if I consider position vector, any vector that is 10i, this is x-axis, 10i plus 100j. If this is y-axis, it will be something like this. That much. Now, whereas the gradient vector is I plus 2xj, then it is I plus 20j, I plus 20j. If that is the case, then if it is 20 times higher to x, it will be like this. If x equal to 2, x equal to 1. If x equal to 1, then the position vector is I plus j. If that is the case, then it is exactly 45 degrees. Whereas the gradient vector is I plus 2xj, 1 plus 2j. Then gradient vector will be like this. Okay, this proves that the gradient vector, what is the gradient vector? If I am at x equal to 1, still there is a slope towards height. Okay, then gradient vector is little bit higher. Looks like gradient vector is tangent. Can you see? This is why I put this example. Looks like the gradient vector is tangent to the point where I am drawing the P. Wherever I am drawing the P, the gradient vector is tangent to it. I am repeating it again. I believe this is very slow tutorial. Anyway, if I have a parabola, equation is y equal to x square. Equation is y equal to x square. Then line equation is x square minus y equal to 0. If that is the case, then gradient vector for the line curve, gradient vector for the line curve is 2x minus 2xi minus j, 2xi minus j. 2xi minus j, we saw that any point if I go with 2xi minus j, it is exactly perpendicular to the point. So if I have a line curve and if I draw a gradient vector is perpendicular to the line curve. But if this line curve is represented by position vector, if line curve is represented by a position vector, if line curve is represented by a position vector, then gradient vector is tangent to the surface. This is what actually I am trying to demonstrate here. So when we have kind of any curve is represented through a position vector, then gradient vector is tangent to the curve. Let's make it more clear with the circle. If I have a circle, then any point P would be represented as xi plus yj, the same we did in the parabola. Then it is xi plus a square root of a square minus x square j. If that is the case, then gradient vector differentiation along x-axis, if I take the gradient vector x-axis not differentiation along x variable, then it will become like x, the position vector is xi plus yj, xi plus square root of a square minus x square j. If I derive it with x, then it becomes I plus minus x by square root of a square minus x square j. If that is the case, then what is gradient vector at any point P? So consider that x equal to if this radius is 2, then x equal to 1. If x equal to 1, then position vector is xi plus square root of a square minus x square. X equal to a by 2, a equal to 2. So x is a by 2 means 1. So x, the position vector is I, xi means I plus square root of 2 square minus 1, that is square root of 3j. Okay. Now if I go with the gradient vector means we calculated differentiation of a position vector. Okay. If I go with the kind of gradient of this vector, then it is xi plus square root of a square minus x square would turn up into I minus x by square root of a square minus x square j. When x is 1, then it becomes minus 1 divided by 4 minus 1 divided by square root of 3 into j. It is really difficult, right? Okay, we try another way. Okay, let's try in polar coordinates. Let's try in polar coordinates. So any point P in polar coordinate system can be represented as a cos theta I plus a sin theta j. X is nothing but radius a cos theta. If this is x axis, any point on x axis, if this is x axis, if I take any point x, if this is a radius a and angle theta, if this is radius a and angle theta, a cos theta is x. So any point P, that is xi plus yj, can be represented as a cos theta I plus a sin theta j. Consider a as 1, radius as 1. It is cos theta I plus sin theta j. This is the position vector of any point on the curvature or on the kind of on the circumference of the circle. Xi plus yj, cos theta I plus sin theta j. If that is the case, then for this vector, if I take gradient mean derivation, then it becomes minus sin theta I plus cos theta j, minus sin theta I plus cos theta j. If I do dot product of these two, then it will become cos theta cos theta minus sin theta plus sin theta cos theta. It becomes 0. This proves that gradient vector, if gradient of any vector, if this is a position vector, then gradient of that vector is perpendicular to it. If it is a circle, if it is a perpendicular to it, then we have already proved that in a circle, the the arc is perpendicular to the gradient vector. If I have arc equation x square plus y square equal to a square, where we took as dfy by dy, and then we saw that arc is perpendicular to the radius. Here, if I am saying if I have a position vector and gradient of this position vector is perpendicular to the position vector, then I have gradient along the curve of the circle. What we are getting? So much time we have wasted, kind of, right? What we are getting? We are getting here that if I have whatever gradient you calculate, it will be perpendicular to it. If you have a line equation, and then you calculate the gradient, then gradient will be perpendicular to the line. If it is a line equation, x square plus y square equal to a square, or y equal to a square root of a square minus x square, this is very crucial information. If y equal to square root of a square minus x square, if I calculate gradient vector of a line curve of a circle, then gradient vector everywhere it will be perpendicular to it. But if I represent line curve as a position vector, then position vector's gradient will be perpendicular to the position vector and it will be curved back. So gradient vector is a kind of relative term. If you have algebraic equation and you are calculating gradient vector to it, then gradient vector will be perpendicular to the gradient vector will be perpendicular to the algebraic curve. But algebraic curve, if you represent through the point P as a vector, and then for that vector, if you calculate gradient, then that gradient will be along the curve. This is what I am trying to prove. So let's consider that curve vector is xi plus yj for the circle, then xi plus square root of a square minus x square j. If I calculate the gradient, that it is I minus x by square root of a square minus x square j. If I do the dot product of these two, then it becomes x minus x, again 0. So this proves that I am not saying that the gradient vector of a position vector is always perpendicular to the gradient vector, always perpendicular. If I have a position vector, if I have a line equation, the every point on the line P, if I represent it through position vector, then if I calculate gradient to it, not necessarily that it will be perpendicular to the position vector, but the gradient vector will always be along the curve of the equation. Here, the gradient vector is gradient of the vector is perpendicular to the vector. This proves that the position vector is perpendicular to the curve. Okay, so that is the scenario. Now if I take the parabola case, and in the parabola case, if I have position vector like this, then at each position vector, if I calculate the gradient, then at each point in the position vector, the gradient vector is nothing but along the curve it will go, if it is a position vector. But if I take the curve and calculate the gradient vector of the curve, then it will be perpendicular to the curve equation. We will proceed on it. It is very interesting. So it is always a matter of confusion that this is 2D. 3D we will see that how gradient vector move on and what drama it does. So that thing, that kind of something that will be very special, that we will take for the sphere and will take for the paraboloid. So those cases, like we have the sphere ready, So we have taken example of parabola, and we took example of kind of uh, parabola and circle. So instead of circle, we'll take example of a sphere, and instead of parabola, we'll take example of a paraboloid. So that is the idea that we will proceed upon, and we will really see that if I have algebraic equation, then gradient vector is perpendicular to it. So perpendicular to the algebraic curve. If I represent algebraic curve as a position vector, then it will be tangent to the curve. Very crucial information that we will share it in the 3D. So whatever confusion people carry, we hope that it will get solved. So we'll proceed in the gradient vector in the 3D.